Everyone nowadays, they're talking about GPUs. ChatGPT, for example, runs on GPU. If you want to use image generators, they run also on GPUs. Entire AI data centers are filled with them. For a while, it looked like GPU has already won. Then some new trend happened. Google, for example, built TPUs. Apple added neural engines to iPhones. Intel, AMD, Qualcomm, and Microsoft, they started talking about NPUs. So you might ask, if GPUs are already so good at AI, why is the industry spending billions of dollars building entirely new processors? If you are watching ML Guy for the first time, in this channel we try to go deep underneath of every complex system to understand how they work. So if you like such content, don't forget to subscribe to the channel and like the video to help the recommendation system. So let's back to the topic. The answer is that GPUs, TPUs, and NPUs are not solving exactly the same problem. When people hear artificial intelligence, they imagine language, creativity, reasoning, and decision making. But underneath all of that, modern AI spends most of its time doing something surprisingly repetitive. Simple multiplication. Imagine a giant table of numbers multiplied by another giant table of numbers. Then imagine doing that again and again billions of times. That's, to be honest, a simplified description of what happens inside the neural network. Each layer receives a number, multiplies them by learned weights, and produces new numbers. The mathematics is not necessarily complicated. The challenge is the scale. A large model may contain billions of parameters and require an enormous number of multiply and add. So the hardware problem becomes simple to describe. How can we platform massive amounts of tensor math as quickly and efficiently as possible? For years, the best answer was the GPU. GPUs were not originally created for artificial intelligence. They were built for graphics. Rendering a game requires applying similar calculation to millions of pixels and vertices at the same time. That pushed GPUs toward a very different design from traditional processors. Instead of a small number of sophisticated cores, a GPU contains a huge number of simpler execution units. A GPU is not designed to solve a few complicated tasks one after another. It is designed to solve thousands of similar tasks in parallel. That made GPUs the natural platform for deep learning. They were another advantage also for GPUs. They were flexible. In the AI area, the research changes constantly. For example, new model architecture appears. New layers are invented. Then at some point, new attention mechanisms are tested. Because GPUs are programmable, developers can adapt them to new workloads without designing a new chip every time. That's why GPUs remain dominant in AI training and are widely used for inference as well. But that flexibility comes with a cost. A GPU must support graphics, simulations, video processing, scientific computing, and many other workloads. Not every part of the chip is dedicated to neural networks. So the next question was obvious. If AI spends so much time performing tensor operations, why not build a processor specifically for tensor operations? This exact question led to the TPU. TPU stands for Tensor Processing Unit. Google designed it specifically for machine learning workloads. It's not for gaming, it's not for graphics, it's only for tensor computation, as the name also shows that. Google was already running machine learning across products such as search, translate, recommendation system for you to use, as the same AI algorithm suggested this very video to you, and thanks for choosing this video. And at that scale, even a small inefficiency becomes expensive. And Google faced a major problem. The processor was not only spending time calculating, it was spending huge amounts of time and energy moving data. This is one of the most important ideas in AI hardware. Moving numbers can cost more than multiplying them. The weights must move from memory to the processor. The activations must move through the model. The intermediate results must be stored and loaded again. Even an extremely fast computation unit becomes useless if it spends most of its time waiting for data. TPUs were designed to make this movement more efficient. One of their central ideas is systolic arrays. Imagine a grid of small processing units. Data flows through that grid like products moving through an assembly line. Each processing unit performs a small multiply and add operation, then passes the result to the next unit. Instead of repeating loading the same values from the distant memory, the architecture uses data as it travels through the grid. It creates very high throughput for matrix operations, but a specialization always creates a trade-off. A TPU can be extremely efficient when workload fits its design, and that's clear, of course. A GPU is generally more flexible when workload changes or contains unusual operations, but both are commonly associated with data centers. What happens when AI needs to run inside a phone or laptop? That is where NPU enters the story. NPU stands for Neural Processing Unit. Unlike TPUs, NPUs are commonly integrated into consumer devices. NPU is not there to train a massive language model. It is there to run smaller AI workloads. Think about face recognition, for example, or voice transcriptions, live translation, and camera enhancement. These kind of workloads introduce different constraints. A data center can provide enormous amount of power and cooling. A phone cannot. Your laptop cannot just take off and fly. You cannot just connect your laptop to the power grid. Battery life in those devices matters. Heat, privacy, and latency also matter. Sending every request to the cloud also introduces network delays and requires sharing data with the remote server. And NPU solve this by executing supported neural network operations directly on the device. Compare it with powerful GPU. It often consumes much less energy. The goal is not necessarily the highest possible performance. The goal is a strong performance per watt. An NPU may quietly process camera frames or model tokens in the background without draining the battery or heating the device. That is why almost every major chip company is investing in NPUs. As AI becomes a standard feature in consumer products, more computation needs to be happen locally. NPUs make that practical. The difference is now easier to see. A GPU prioritizes flexibility. It supports many kind of parallel workloads and remains the most widely used platform for model training and large-scale inference. A TPU, on the other hand, prioritizes specialization. It's designed to execute tensor operations with high throughput and efficient data movement, particularly inside machine learning infrastructure. An NPU prioritizes energy efficiency. It brings AI inference into devices with limited power and thermal budgets. None of these processors are universally better than the others. They exist because training a frontier model in a data center is not the same problem as running face recognition on your phone. Different environments create different bottlenecks, and different bottlenecks create different hardware. Until the next video, good morning, good afternoon, and good evening. Bye.